So now we're going to do some example problems from section 2.2. So first, finding zeros of a polynomial function. So find the zeros algebraically using graphing utility, graph the function, and use the graph to approximate the zeros, compare them with those in part A. Okay, so what I'm going to do is algebraically, it means that we're probably going to have to, well, here's what I would do. This is quadratic. I noticed that 5, 10, and 5 goes evenly into all three, which means that I can pull out said 5, right? And I end up with that, which means that it is much easier to factor, right? Meaning I'm looking for two numbers that multiply to get 1. Oh, wait, that's 1 and 1, and that's it. But add together to get a -2. So how's this going to work? Well, how can we do that? 1 times 1, 1 minus 1. So here's the problem. If I try this, that doesn't work because negative times negative is positive. That's not positive. If I want like that, does that work? No, because then I get -1 plus 1 is 0, but I want a -2. So it turns out I can't actually factor this. What a bummer. Okay, so what do I do then? If I can't factor it, does that mean am I doomed? No, I resort to the quadratic formula. Now, if I pull this 5 out, then I can just find the roots of what I'm left with, meaning it's actually going to be easier. So opposite b, or positive 2, over 2 times a, which is 2. 2 times 1, right? Plus or minus, well, this is going to be over 2. B squared, so that's 4, minus 4 times a times c, or 4 times 1 times a -1. 4 times 1 times a -1. That -1 is kind of key because I'm going to get, well, 2 over 2 is 1, plus or minus the square root, well, that's 4 plus 4, or 8, right? Because of the negative, it ends up being 8 over 2. So the zeros are at 1 plus, now the square root of 8, plus or minus, the square root of 8 can be reduced to 2 root 2 over 2. So we would say that the zeros are, because the 2's cancel out, 1 plus or minus the square root of 2. Now remember, the square root of 8 is the same as the square root of 4 times 2, which means I can take the square root of the 4 individually, which is 2, times, well, I'm left with the 2 left over here, so that is 2 root 2. That's how that happened. So we'd say that the zeros are 1 plus or minus, so that's what the zeros are algebraically, 1 plus or minus, so there's 1 plus the square root of 2, and 1 minus the square root of 2 are these zeros. X equals that. So if you were to graph these, use the graph to approximate 0. So if you were to use Desmos, by the way, this is 1 plus 1, square root of 2 is about 1.4, so that's going to be about 2.4, right? And 1 minus 1.4 is going to be 1 minus 1.4 is going to be right around -0.4. And that's what you should discover are the approximately what the roots are. Okay, this next one's a little bit prettier to the extent that we can actually factor it. Now, first off, 1/4 x cubed. 1/4 x cubed. You should recognize that that x, which is the same, x by itself is the same as x minus 0. So one of the zeros is x equals 0. So that's one of the roots. And x squared minus 9, that is a difference of perfect squares, or two numbers that multiply to get a -9. So one's going to be positive, one's going to be negative. 1 and 9, or 3 and 3. How do you pick? Well, there's no center term. In other words, there's a 0x in there, right? If you look carefully, which means they need to add to get 0, which means -3 and +3. So our roots are 0, 3, and -3, or 0, -3, and 3. It doesn't really matter what order you put them in, okay? And if you were to graph this, guess what? It would look like that. By the way, as a little adjunct, if you look at the graph, right? Multiplicity 1, multiplicity 1, multiplicity 3. Get it? Get it? And this is cubic, and that's positive. Or sorry, that's cubic. This degree, that's degree 2. So this is a 5th degree polynomial, and it is a positive coefficient. So it's 5th degree, and it's a positive coefficient, which means from left to right, it's going up like that. So when you graph this, it should look something like -3 and 3 and 0. So it's going to start down here, cross straight through, do the little squiggle, and cross straight through. So your graph should look like that, assuming you use Desmos correctly. All right. Finding zeros of polynomial function. So find them algebraically and then compare. I'm going to assume that you guys can compare. So let's just do the algebraically because that can be tricky. First off, I see a common factor. In other words, I can pull a 5 out, meaning divide by 5 and hope that that does something for me. So now I've got this. Now, here's the deal. How do we get x to the 4th? Because we have x to the 4th and x squared and then a numeric term. So this only works if in this case, but what if I had an x squared and an x squared? That means I'd get my x to the 4th, and then I'd have x squared times something and x squared times something. That would give my x squared term. Am I lucky enough for this to be factorable? In other words, what times what is 2? Well, the only options are 2 and 1. Because it's positive, they're either both negative or both positive, but they're adding to positive, so they better be positive. Does this work? Well, yes, it does. Now, what does this mean? It means that we're close to finding the zeros. Remember, those are x squareds, which means they're not -1 and -2, but it does mean we're on the right track. It means that either x squared plus 1 equals 0, or x squared plus 2 equals 0, right? Those are how we find the zeros, which means that when we subtract 1 from both sides, it means x squared equals -1, which means x equals the plus or minus the square root of -1. Wait. Or in this case, we get x squared equals -2, and x equals plus or minus the square root of -2. So at this point, little flags should be going up. So wait a second, this thing has been what? It's been, we can't take the square root of this. If you remember, right, that's plus or minus I, the square root of -1, and this would be plus or minus I times the square root of 2, or square root of 2i actually. But either way, those are imaginary numbers, so those aren't actual real zeros. So when you graph this, what does that mean? It means it never hits the axis. So I'll leave it up to you to graph this and show that there are actually no zeros to this particular one. Okay, finding zeros in the multiplicities. So find all the real zeros, determine the multiplicity, and then use a graphing utility to verify your results. Okay, so crossed fingers. There's nothing that goes evenly, so let's hope that this is factorable. What times what is 25? Well, 5 and 5 come right to mind. Adding together to get 10, so plus 5 and plus 5, right? Is that the same as saying x plus 5 squared? Yes. So what does that mean? This has zeros. This has a 0 at x equals -5 with a multiplicity of 2. It's repeated twice, right? Which means that the graph should look like here at -5, and it should, because that's positive, open up, it's going to bounce, right? Now, this next one is mildly tricky. Do you see a common factor? You should be looking for common factors because x to the 4th, x cubed, x squared. I could pull an x squared out of there. And if I did that, I'd be left with x squared, because x squared times x squared is x to the 4th, minus x cubed times, well, x, right? X times x cubed. And minus, well, if I pull that out, then I'm just left with a 20. Which means I've now got a quadratic that we hope we can factor. So what times what is -20? Like a negative and a positive, but adds together to get a -1. So with a little bit of experimentation, we end up with that. So we have a 0 at x equals 0, multiplicity 2, because it's squared, and zeros at x equals positive 5 and -4, multiplicity 1, because they're just repeated once. That's it. Finding a polynomial function with given zeros. This is actually easier than you might think. You just have to be a little bit careful. Find a polynomial function that has the given zeros. There are many correct answers. When they say that, they mean that there is some value of a, right? The vertical stretch, which could be positive number, it could be any number, right? So in other words, a could be anything. Most people just set a to 1. In other words, they don't bother with it. So how do we reflect negative 2? With a plus 2. How do we reflect negative 1? With a plus 1. How do we reflect 0? We just x by itself, and then x minus 1 and x minus 2. That's it. You're done. Once again, a could be any number. It could just be 1, or it could be 2, or it could be negative 5, or 3 billion, whatever. Now this next one's a little bit trickier, but there is a preferred way to write this. So now we've already used f, let's use g. So we know that this first 0 is x minus 3. That's easy. Deep breath, right? What about the next 2? Well, 2 plus root 7 is just a number, but I don't want a decimal. I want to be exact. So I'm going to say x minus there. Remember, it's always x minus whatever the root is. Well, if the root is that, then it's x minus that. And same thing here, except instead of 2 plus root 7, it's going to be x minus 2 minus 7, 2 root 7. Now, I just leave it like that. Don't bother. You're done. The many comes from this could be positive, could be negative, could be any number in front of there. Okay? All right. Find a polynomial function with this given zeros, multiplicity, and degree. When it says the many answers, it means that there is a multiple a in front of there. That could be any number, right? Positive or negative. So 0, 3, meaning x minus 3 is a factor. Multiplicity 1, don't do anything. 0, 2, x minus 2. Multiplicity 3, degree 4. 1 plus 3 is 4. There, that's a possible answer. 80. 0, 1 at multiplicity 2. 4, multiplicity 2, degree 4. 2 plus 2 is 4. Falls to the left, falls to the right. Okay, what does that mean? So as you're looking at the left and right of this graph, right, we know that because it's degree 4, either it's going to look like this or it's going to look like this, right? How do we pick? Falls to the left, meaning goes down. So that, I would argue that it's this where it's going down, right? What does that mean? It means that there must be some sort of negative. In other words, it's got to be reflected. So one way, if you want to really be sneaky, then you could cover all the bases, that is all the possible answers, by putting that as a, and you could say a has got to be less than 0. In other words, a has got to be negative. Okay? But it has to be negative, otherwise you don't get the falls to the left and falls to the right. Okay? All right. Sketch a graph of a polynomial that satisfy the given conditions. If not possible, explain your reasoning. So 4th degree polynomial with 2 real zeros and a negative leading coefficient. So 2 real zeros. So 2 real zeros, meaning just 2 numbers, right? 2 real zeros and a negative leading coefficient. So if it's 4th degree with a negative leading coefficient, it's going to be down here, and 2 real zeros. So could it be, well, if it's 4th degree, could it be, well, I don't know, could it do this and then this? Would that be a possibility? Let's think about that. Could that be 4th degree? Well, for instance, what if it were x to the 4th, which is our most basic 4th degree model, but let's say I shifted it up, I don't know, 4, and I put a negative in front of there because it's, negative leading coefficient. So that would work. Are there other possibilities? Well, could it have 2 zeros, right? But instead of crossing through, could they bounce? Like that, right? Sure, that's a possibility, right? Isn't it? So it turns out that there's a couple different ways to do this, but those are a couple possible answers. Key thing, they must open down because of the negative leading coefficient. And has to have 2 real zeros. Hey, this is the same question. That's interesting. Interesting for it, not so interesting for us. let's do 86 instead. So here we're going to do this. We're going to sketch the graph of the function by applying the leading. So what we're going to do is we're going to sketch a graph of this. So when you're looking at this, it is indeed quartic, but I'm going to pull this out because I get that. So remember, look for common factors so I can pull the x squared out, because then we can indeed factor that. -4 means +2, -2, and together is no center term, right? Now, what does this mean? We've got well, what degree is this? It's 4th degree. We already talked about this. This is positive. So that means as x goes to positive or negative infinity, y goes to positive infinity. That's what they're calling the leading coefficient test. That is the number in front of them, right? So we know that this thing is going to have zeros at 0, right? 2 and -2. This is multiplicity 2, so it's going to bounce. Multiplicity 2, and these are both multiplicity 1. We know that because of the leading coefficient, right, that this has not been reflected, so it's going to open up. So we know that either end is going to look like that. So it's going to come through, bounce, come through. That would be our sketch. Okay, nice W-shaped graph. What? Last, but not last. Well, it is last. All right. So if I see a negative coefficient, I like to pull a negative out. What does that do for me? It changes the signs of stuff. That's a cubed minus 8, right? That means if I'm factoring it, I don't have to worry about, you're right, I can factor this. And this is similar to the x squared and the x squared. X cubed times x cubed works out to be x to the 6th. And this one, well, then I can get that center term because I'll have some two numbers. How do I get a -8, but then when add them together to get a -7? Well, I would argue a -8 and a +1, right? Okay. Now this, brace yourselves, this is not going to be pretty. So this is a 6th degree model, 6th degree. With a negative leading coefficient, right? So 6th degree, that means it's going to open down, right? And what else? Well, it means x goes to positive or negative infinity, y is going to negative infinity, even degree, both opening down. So what are the zeros? This is where it gets a bit tricky. So we've got a couple of different problems going on here, but this means that we're looking at when is x cubed minus 8 equals 0, and when is x cubed plus 1 equal to 0. Now when you solve this, it means that we've got x cubed equals 8, or x equals the cube root of 8, which is cube root of 8, which is 2. And we've also got, in this case, same idea, we subtract 1. We take the cube root of -1. Now, it is possible to take the cube root of -1. You don't believe me, try on a calculator. And in this case, you get -1. So this has 2 zeros. And it means and we're going to learn about how to do this in the next section, but we could pull that 0 out and figure out what the other this is, because this has a factor. There's going to be this x cubed minus 8. We can break it down, so we'll end up with this negative. And we'll have a 0 at x minus 2. And then we'll have some quadratic. We don't know exactly what that quadratic is, but we're going to have this quadratic left over after we pull out that single 0. And then we're going to have this 0, which is x plus 1, right? And then we're going to have this here, which is going to be another quadratic, but it's going to be different. But that's when we pull that out, okay? Right. Now, it may be that this quadratic is factorable. It may not. Let's try something. As a matter of fact, let's try something for both of these, just in case. Now, I happen to know that 2 times 2 times 2 is 8. So let's try this. X minus 2, x plus 2, x minus 2. Negative times positive, that doesn't quite work. But could this be negative? right? So what I'm trying to do is break this cubic down into something. Now, the only problem is, and I want the center terms to cancel out, and I just don't see it happening. Because when I distribute this, I'm going to get x squared minus 4x plus 2. And when I distribute this, I'm going to double down. So that's not actually it. That's not going to work, all right? So this is going to be some quadratic. We're not sure what it is. So we're just going to have to kind of leave it that way. What about this x cubed plus 1? Is that possible? So if I have an x plus 1, could I have like an x minus 1 and then another x minus 1? So I know that these are going to become x squared minus 1 together, but I'm going to multiply this by a minus 1, so I'm going to x minus cubed, right? But I'm going to have a minus x and a minus x squared, so that's not going to work either. So I'm pretty confident that what we've got are 1, 2 zeros, right? We've got this 6th degree model where the end behavior is going to be here and here. It's going to have a 0 at -1 and a 0 at 2, right? -1 and 2. And it's going to cross straight through. Is it going to do other stuff? Yes. I'm not sure exactly what the graph is going to look like. I mean, we could run that up on Desmos and see. But if you actually run that, then you get something that probably looks similar. Let's take a quick look. And we have negative x to the 6th plus 7x cubed plus 8. And indeed, we get some weird behavior going on here, but we do get those two roots, one at -1 and one positive 2 as promised. So this is not the greatest problem because we don't know exactly how to find this, but we should be able to at least figure out that it's got these two zeros. Okay? This concludes our examples from section 2.2.